So for today, you'll be doing box plot. We will look into different graphical representations, but you will do some exercise on box plot. Okay, so in this lesson, the whole idea is to introduce some graphical display and interpretation of graphs. So there are different graphs that you can display your data, such as stem plot, box plot, and histogram. So you are to calculate some quartiles, mean, median, and mode, and you have to also know what is variance and standard deviation. So now we are moving into descriptive statistics. This is called descriptive statistics. These calculations that I just mentioned, quartiles, percentiles, mean, median, mode, variance, standard deviation. Of course, there's more to it. There's like kurtosis, skewness. Actually, in your Excel, right, when you just tick the boxes, it will give you all the measures. Okay, but I'm fine with you using Excel, where you don't have to go through these calculations by hand, but it's important for you to know what it means. Okay, that matters, because we are moving towards gadget kind of industry. So you don't still have to press your calculators, but use the software. Learning to use the software is actually a good skill for you, even if you master your Excel, because Excel also have VBA, Visual Basics, which also can be used for machine learning. You can use VBA for machine learning, and then there's also pivot tables, which are very desirable for industries. Okay, so if you pick up Microsoft Excel, it's actually a good skills for you as well as an engineer. So descriptive statistics are numerically and graphically describe and present the data. And to display data, we have different types of graphs. We have dot plot, bar chart, histogram, stem and leaf plot, and so on. So some of it you would have been exposed to in high school, but some of it can be something new. So I think box plot, I focused on box plot previously because it was not widely used, but now students actually told me that they've started using it in schools as well, which is good. Okay, which is actually an advancement. So some of these graphs are being explained in these slides. Okay, so we have stem and leaf graph. So what happens if you have numbers, like for example, very related example is your matrix number. Okay, numbers like this. 33, 34, 35, 36, 37. So the 3 is always repetitive. The main number, the first number is repetitive. And then you have a number behind it. Okay, so for example, if I take these numbers, if I look at 4, see I have 4, 2, 9, 9, which is representing 42, 42, 49, and then there's another 49, 42, 49, 49. That's stem and leaf. So for your matrix number, now it has changed, but probably you have numbers in front like 17 or 16, then you have 4 digits at the back. Those are your leaves. So you'll have a stem and then you'll have your leaf. Okay, so that is stem and leaf plot. Okay, so it gives you, see, immediately you can see a pattern, which one has a higher frequency, which one has more frequencies. Okay, then you have line graph. Usually the x-axis consists of data, y frequency. Okay, line graph means this line is like, it's like a bar chart, but then it looks like a bar chart. It can be a bar chart also, but it's a line graph because it's a straight line to that point, to this point. Okay, number of students, cups of coffee, it's a line graph. Then you can have bar graphs for the same daily consumption of coffee, like I just mentioned. Okay. Okay, this is another bar graph. Okay. Then you also have histogram. This is bar graph. Okay. Please notice it is standing on its own. It is referring to a discrete number, and it is also separated here. Okay, these points are separated, which shows that it is it is separated. It has discrete numbers here. Okay, it's discrete. It's not 1.5. You don't have 1.5. You only have 1 or 2. Okay. Also, it doesn't show continuous. You have until 25. 13 to 25. The next number is 26. There's no 25.5. Okay, this is a bar graph, and whether it should be close together or not is dependent on your discrete or continuous. Your age group can also be continuous if you're talking about months. If you treat it as a continuous, then you are probably going to have a bin here. This is 25. Here it will start from 25 to 44, but here you start from 25.01, 25.02 here. Then it will join. That's the difference. Okay, so this one is bar graph when it's separated. A histogram consists of continuous boxes, and it is usually, where is it? Did I mention it here? It's usually a continuous. See, it's still, this is not joined. So if it is not continuous, it will not be joined. Data of height for 100 sockers. I think this is joint. This is just to show this point, because they draw this point. It has got a line here. Okay, so these are different classes. So this is a continuous information. So they show histogram. It's connected. When it's connected, you use histogram, because these lines are connected. Okay. Those three charts that we have seen. Then you have box plot. So why box plot? I focus on box plot in our class because when you have a lot of data, we use box plot to explain the data to us. And even if you're working on experiment, the box plot will actually give us information on where the data, what is the median of the data, where it falls, what is the lower quartile, what is the higher quartile. So you get an idea immediately from the box plot. So most of our experimental work also uses box plot. So that's why I will be focusing on box plot, because we'll be using it later for that experimental optimization. Okay, so box plot gives you all this information in a glimpse. In one glimpse, you'll be able to see the minimum value, maximum value, and all the quartiles, median, 25% and 75%. And if you have outliers, you can also see it. And then it gives you an average as well. This is median. Median is a middle point. Average is the mean value. So this is an example of horizontal. This is a horizontal, and this is a vertical box plot. So this is the mean value. This is the outliers point. Okay, this is the median, 25%, 75%. Okay, so this is other informations that we can get from box plot. Then this is how we calculate interquartile ranges. Okay. Okay, interquartile range is a number that indicates the spread of the middle half of the data. That means it is the difference between third quartile and the first quartile. So it gives us how spread the data is. Okay, interquartile ranges. So I'll show you in the plot, because otherwise just like this it doesn't explain much to you. Then you also have outliers. Outliers are 1.5 interquartile range below the first quartile, and it should be okay. Outliers means you have a box plot. You have a box plot, and then your data falls outside these lines. Outside these lines. Okay, outside. So when it falls outside, it's outlier. So even if you run an experiment and then you collect your experimental information, it may not fall within this range. It may be slightly outside here. It's in the interquartile ranges. It's still acceptable. That means your experiment was not wrong, or you did not have mistakes, or it's not a mistaken data. It's still acceptable to be 1.5 above the interquartile range. Okay, but if it is outside this value, you should remove that data. You should not use that data, even if you're experimentally correct, but it was statistically unhealthy. Okay, but again, as an engineer, this is a simple statistical descriptive information. For you to get a good outcome, you must remove it. But something that is outside can actually lead you to solving some issue as an engineer. When you think as an engineer, when you have a lot of information as an outlier here, then there's some problem that you need to address to reduce that outliers. So that is a critical thinking that you apply to a simple statistical information. Okay, maybe next week I can show you some examples of that, because I do machine learning for PM 2.5 prediction, and I have got a lot of data for outliers. So when I check out what these outliers are, that was the season that we had haze. So when we had haze, there's more 2.5, which is outside the normal range of the PM 2.5. So since I'm doing the prediction of PM 2.5, I cannot remove that information, because that is a true information. It's just that haze is an event that occurs. So I still want to include it in my prediction work to find out what changes of other parameters can bring about PM 2.5. So that's one of the cases where if you have outliers, it can actually deliver some information to you. We still have to address it. Okay. Right. Okay, so this one, okay, so that was outliers, right? Outliers should be beyond the 1.5 beyond the first quartile, and 1.5 beyond the third quartiles are outliers. Okay, so this is an example of how you calculate interquartile range as well as outliers. So when we have house price in 2010 as such, okay, you find the median. So you arrange it. So when you arrange, median is the middle point. Then you find your quartile 1. Okay. Then you find your quartile 2. And then you have interquartiles between this quartile 1 and quartile 2. And we find the outliers range. Okay, outliers range.